Hello, guys. Do you have my voice? Just nine students. Are you there?
Geliyor hocam sesiniz.
Semra, Fatih. Yes, thank you, Tibyan. You are here again with me. Um, Let me share my screen for our heat equation and cover the missing topic. Pardon, çocuklar. Sorry, just need a minute. Okay, guys. Um, Good morning again, everyone. In the previous lecture, we studied wave equation. Sorry. We studied wave equation, and in the wave equation, we saw how disturbance travel through a medium. Today, we move to another fundamental partial PDE, the heat equation. Unlike waves, heat actually does not propagate as a moving pulse. Instead, temperature differences gradually disappear until equilibrium is reached. By the end of today's lecture, actually, you will understand what a heat equation is and how we solve it in a simple way. Again, there are lots of type of heat equations. Some of them are really complicated to solve, but we just will cover the basic version, and we will use separation of variables techniques, and we will also cover the different types of initial conditions for this problem, like with the wave equation. Okay. Remind that this was the wave equation models, and wave equation models propagates, which means that actually if you have a wave, then from to the right and also left, these waves just propagate to the right and left, and we analyze the mathematical equation of this problem. But here, the heat equation in this class, in this lecture note, the heat equation models a completely different phenomenon, another problem. U sub t is equal to a constant times uxx. And if you analyze the difference between wave and heat equation, then you see that for the position variable x, we have both the curvature second level differentiation, but for time here we have ut here. In the wave equation, we talk about disturbance travel through the medium, but in the heat equation, we will talk about temperature differences. They will gradually disappear. They will catch an equilibrium, and we will discuss about heat equation in this way. If you are considering about heat, it's a simple fact for all of us that heat will flow from hotter regions to colder regions, and at the final case, you will reach an equilibrium between hot and cold. So the heat equation is a fundamental example of parabolic PDE, which means that if you do a delta analysis, your delta will be zero in the parabolic PDE. Uh, the classical heat equation problem, you just consider a thin homogeneous rod of length L. As you see, the length is L for our rod. Then it's thin and homogeneous. Of course, there are some complicated problems to analyze. What if it is not homogeneous? What if it's not thin, but it's more big? So in this case, we denote the temperature by Ux of t. So our unknown function in PDE defines our temperature here. Here, x represents the position, again, like the wave. X represents the position along the road, and t represents the time. Okay, t represents the time in heat equation. Our goal is simple here. Given the initial temperature distribution, we need to determine the temperature everywhere at any later time. So after 10 seconds, for example, what will be the temperature at the beginning, also at the middle, maybe at the final position of the, or just any position on the road. For any x, we will make a this we will make it guess about the position x, time t, and what is the corresponding temperature. This is the heat equation problem, okay? Of course, there will be a hotter region, there will be a colder region, and we will reach an equilibrium point between them after a while, okay? After a while. So this is the physical problem we are discussing in heat equation problem. What is the mathematical model of the problem? This is the mathematical model of the problem. Ut is equal to a constant times uxx. This is one-dimensional heat equation. In a heat equation, again, temperature and the position will always exist, but there may be some other, maybe x, y, z, or any other extra variables. So the heat equation dimension can be 2, 3, or more. But in our class, we will cover just only one-dimensional heat equation. So just position index x represents position. For the road, we just consider a road of L from 0 to L, the length is L, and also T is represented time. Here, K is constant and name test thermal diffusivity. As you see, there is only one derivative with respect to time. There is no UTT in our heat equation. And the first derivative tells us that the present rate of change depends on the spatial curvature of the temperature profile. Here, the constant K is called thermal diffusivity, we called it. Actually, larger values of K mean faster heat diffusion. If you have a larger K, which means that heat diffusion will be faster. So in a short time, in a small T value, the equilibrium will be reached. Okay, will be reached. Some books use the notation since K is greater than 0 all the time, thermal diffusivity, then it can be shown by a C square or some other square terms. Initial condition to obtain a unique solution. Actually, we must satisfy the initial temperature. Initial temperature means that actually you attain a 0 for your T and it gives you the initial temperature f of x function. Of course, f of x can be constant value. For example, initial temperature can be 0 or any other degree. Since the equation again contains only the first derivative with respect to time, I mean with respect to time derivative, only one initial condition is required with respect to time. So since you have just only one first order derivative for t, one initial condition will be required in this problem. This initial profile describes the temperature distribution at the beginning of the problem, at the time 0, I mean, okay? At the time 0. What about boundary conditions? Boundary conditions describe what happens at the ends of the road. For example, if this is the road, at the beginning, these are the ends, and at the end, at the position 0 and at the position L, for the beginning and the final point, it describes what happens there. For example, if we consider Dirichlet condition, we discussed the similar conditions in wave equation also. If your two condition includes only the unknown function u with some variables or values, then these conditions name test Dirichlet. if the unknown function, I mean the boundary conditions given with the first order derivative values at some values, as you see at x0 and at x is equal to L at any time L, anytime t, then these conditions names as Neumann conditions. In the Dirichlet, physically, which means that both ends are kept at zero temperature. So here zero temperature, but of course at some other points there are some other temperatures. So we try to catch an equilibrium there. Okay. Neumann condition specifies the heat flux through the endpoints. So it uses the first order derivative. In the mixed order derivative, in the mixed order derivative, we can say mixed boundary conditions, or sometimes we say Robin. Okay, these are called as generally the Robin condition. We can say that sometimes at one endpoint is kept at a fixed temperature while the other is insulated. So it shows you that mixed boundary conditions appears there. As you see, the unknown function u, but the derivative of u with respect to x. Okay, so we combine the Dirichlet at one endpoint and Neumann at the other endpoint. In this Robin problem, a different physical situation actually lead naturally to different boundary conditions. Of course, it's more complicated. We generally deal with Dirichlet, but of course, by the same algebraic process, Dirichlet instead of Dirichlet, Neumann or Robin can be used also. Okay. Some of the books say it's not Robin, but mixed boundary value problems. Anyway, the model problem, ut is equal to k times uxx. Throughout this lecture, we will solve just this one in algebraic form by using with homogeneous Dirichlet boundary conditions. Why? Actually, because the boundary conditions are homogeneous, and then we may use the method of separation of variables to solve it. Otherwise, if we didn't use the homogeneous form, then some more complicated solution methods must be used, but we will not cover them. So we are just dealing with the homogeneous simple problem. Okay, simple one dimensional heat equation problem. So anyway, our method is separation of variables. We just assume the homogeneous solution. This assumption, actually, you say that if our unknown function is a multiplication of a function depends on x times a function depends on time. This assumption transformed our PDE into two ODEs like we do before. This transformation converts PDE into two ordinary differential equations. Of course, you need to take the first partial derivative for u with respect to t because ut exists in the problem, not utt. So you don't need to construct utt here. This is ux. This is uxx. We just take the derivatives randomly. If you're taking derivative with respect to t, this part will be constant. So you will keep your x, but you will take the derivative of the second factor, t, which we called as t prime. So you get to ut. For ux, you say that this part will be constant at that time. We are keeping t and write that x prime will be the first derivative. For the second, again, this part will be constant, so you will keep it, but the derivative of x prime with respect to x again will be x double prime. Okay, so if you substitute these derivatives into the PDE, remind that your PDE was UT, it will be better to write it. UT is equal to K times UXX. So this part is UT and this part is constant times UXX. So to apply the separation of variables, we need to separate it into two parts. With an equality, there is only depends on the variable x, and the right hand side will be depends on t, or vice versa. It does not matter. So if you divide both sides actually here with x, then x double prime over x will be one of the parts that includes only x. And you will have t prime, you are dividing by t, you're transposing to that part, t prime over t, and also you have k. Of course, you are free to take this k to the part to the t, or here you can keep k alternatively here like that. It does not matter, but we say that this is depends on t, this part is depends on x. So this can be only done by having both of them to a constant part. Say that our constant is lambda, okay? If you say this is lambda square, you are wrong. It can be negative. You cannot know the result. So you need to write a free variable lambda. Here, the separated ODEs can be written as, say that t double prime k t is equal to lambda. So you will conform it into an equality form by doing an inner outer product and transpose to the left. You get the ODE like that. And the second ODE was x double prime over x is equal to lambda. So you can convert it into form like that. Way. Now we will investigate the possible sign of the separation constant delta to analyze it. Okay? To analyze it. Let's analyze the case lambda is greater than 0. For case lambda greater than equal to 0, you need to assume that lambda is can be denoted by alpha square. The solution consists of exponential functions at that time. As you see, because you have like that, which means that your characteristic equation will be like that, and your R will be positive and negative alpha, which lets you to the following solution: C1 times e to the minus alpha x plus C2 times e to the alpha x. We already know that x0 is 0 and xl is 0. How we get that? By using the conditions that are given in the problem. So we say that if you substitute 0 for your x, then you will get a 0 value. And which means that actually getting 0 will show you that C1, C2 is equal to 0. If you do the same for L, again, you will get a 0 and you will obtain another equation, which actually, if you solve them, only trivial solution will exist there. So you say that C1 and both C2 must be equal to 0. We already know the trivial solution exists for our problem, so there is no other extra solution in the case 1. So we can discard this case, actually, discard it, okay? There is no new solution type appears there. What about lambda is equal to 0? Here, our solution will be linear, actually, because you have x double prime is equal to 0. If you integrate it with respect to x, x prime will be just say that C1. And if you integrate it again, then x will be, you can say that C2, C2x plus C1. So anyway, it will be linear by the solution of this one like an ODE. So if you apply the conditions, I mean 0 temperature at the beginning and ending point of the road, then again, you will get only trivial solution here. Again, we obtain the trivial solution, which means that again, we will discard this solution, okay? Because we already know that for a homogeneous problem, we have the trivial solution, okay? And for case 3, which is the actually just one case, the unique case, we will get the result. So we say that we will let our alpha is equal to negative of alpha square. So you get actually r square plus alpha square is 0. So no real root exists. Complex root exists in this characteristic equation, which means that you can write your x solution as C1 times cosine of alpha x plus C2 times sine of alpha x. Applying first boundary condition here removes the cosine term. If you apply the first initial condition, which means that actually you will write 0 for your x, then first boundary condition removes the cosine term. Then after that, the second boundary conditions, if you get first boundary conditions with substituting x is equal to 0. For the second boundary conditions, we will get x is equal to L. X0 is 0, so you get C1 as 0 as the result. So first term, which means cosine term, drop. And for the second order, second boundary condition, which means that you are substituting L into your X but keeping T, then your C2 times sine of alpha L is equal to 0. Actually, this is exactly where eigenvalues appear. Then this condition can be solved by if sine of 0 is sine of something is 0, then the argument will be n times pi. Of course, and can be take the values for 1, 2, and etc. So if you try to know what is alpha, or lambda is equal to minus alpha square, we are trying to get what is lambda. So your alpha is np over L. If you write the x and x solution, which means that for each n you will get another solution, there will be lots of solution there, non-trivial. So sine of and pi x over L will be your x solution as the result of this part. In the time equation, you can say that since lambda is equal to minus alpha square, we get alpha in the previous slide, then your lambda value will be the square of the thing that you found there. If you consider the sign value, then this equation becomes like that. T prime plus k times n pi square over lt. Again, you can separate the variables to solve it. And if you integrate it, then of course we will get here as ln t. It will be minus k, keep the constant, and you are integrating it with respect to t, so you are keeping the constant, but write ln again. So actually you will write the constant, let me write it, times t. But you will also have a constant here. Say that it is ln an, okay? Since this we'll call this tn. So if you just combine them, this will be e to the, this expression will be the core solution of the problem. So anyway, tn is equal to a sub n times this one. If you combine x and t, remind that u is equal to x times t. This was the variable transformation you did as the separated solution. So un is equal to, this is the thing that you found by the solution of t, and actually this part, and an, and this part is the solution of x. So if you combine them, then you get the result. And this is the solution of the heat equation. Okay, this is the solution of the heat equation. But we say that since the heat equation is linear, actually we superpose all modes, because for each n, for n is equal to 1, you get a solution. For n is equal to 2, you get another u1, u2 solution. So by the superposition principle, then we can say that we can add them up. We can update our coefficient to Cn, and we get result from n is equal to 1 to infinity by the keep solution. For example, at t is equal to 0, we obtain the solution, this one. We just substitute as 0 for our t, and we get the solution, this one. Here,
Hocam bir şey
I
yazıyor musunuz
mean, I can
slaytta?
say that Uh, at time 0, the initial temperature distribution must be expanded, which is a Fourier sine series. This is a Fourier sine series. Fourier sine series. Therefore, the coefficients can be found by the Fourier coefficients of f of x here. And we already know that orthogonality is what allows us to isolate one coefficient at a time. By multiplying with another sine function and integrating, every other term disappear. This is exactly the same idea we use in Fourier analysis. So in the Fourier coefficients, actually, we will get from 2 over L, from 0 to L f of x, sine of the same argument that we write in an, I mean the solution of the x part. So we finally can be written, the final solution can be written as this one. This is the Fourier solution actually type. This is the CN coefficients and times the remaining parts. So this is the classical solution of the heat equation, but with homogeneous Dirichlet boundary condition. Otherwise, some complicated solution methods will be necessary, so we are just omitting them in our class. It is enough to understand this theory and how we obtain the general solution like that. If we ask any heat equation in the exam, again, like we did in wave equation, we will say that by deriving the corresponding formula. Remind that in the previous formula we just discussed about that it's D'Alembert solution. It has a special name, and we say that we will ask it as deriving the D'Alembert solution. Deriving means that you need to show all the theory that we get there. So this part is enough for heat equation, but it's a big topic. In any PD title, PD book, you can find a lot about these problems, okay? So this was the missing parts in our previous class. So that's all. Oh, you write something. Funda, I just saw your case. Uh, I finished the class and I see your writing notes now. Evet yazdım, hep açıklamalar yazdım. Arada ara işlemleri gösterdim. Neyse açıkladığımla idare edin. Yani şu ara adımları gösterdim şuralarda. Yani ufakta tabii bir sürü açıklama yazdım. Niye göstermedi ki? Hay Allah ya. Şu an yazıyor mu?
Şu anda
Bakın
yazmıyor
mesela şu
hocam.
anda da karalıyorum ekranı. Görünüyor mu?
Yok, görünmüyor.
Şu an ben chat'i göremiyorum. Çok üzgünüm çocuklar. Yani tekrar paylaşayım ekranı bilmiyorum ki. Neden öyle oldu? Baştan beri ben bir sürü şey yazdım ya. Niye bu kadar geç söylediniz? Açsanıza sesinizi söyleyin bana. Ee, I described the heat equation algebraic form like that. This is a parabolic equation, which means that if you calculate your delta, then you will get the result. I will not talk about this part. These are the similar condition. I write lots of things here. We just use separation of variables. We take the derivative in this step. I just said this is constant and this can be taken derivative for ut. So you get x times t prime. For ux, it is x prime times t by keeping that this is constant. And if you substitute all these derivatives into the original PDE, you get this. And by using the separation of variables, you need to separate into two parts, depends on time and x only. We use the general lambda separation constant. We obtain two ordinary differential equation like that. One is this, one is this. So by possible sign of separation constant lambda, like we did in wave, we just analyze the solution for each ODE. Say that lambda is greater than 0, which means that lambda can be taken as alpha square. We substitute alpha square, the characteristic equation. I write all the things here. We write characteristic equation as r square minus alpha square is equal to 0, which means that r will be equal to positive and negative alpha, which implies the same solution here. By the initial conditions, we get x0 is equal to 0 and xl is equal to 0 by substituting x times tt for the initial condition. Okay, this is your u. If you use the initial condition x is 0, then you will get x0 here. This term will drop with the 0 value. So anyway, if you substitute this, then you will get only the trivial solution exists in this case. So we will discard this case. For lambda is equal to 0, which means that alpha is 0 also in this previous, you will reach the ODE x double prime is 0, which means that actually you will reach by integrating. I integrated in two steps. Here, x prime will be c2. Again, you will integrate it. X will be c1 plus c2x. with respect to x. We integrated twice. So anyway, this is the solution. If you apply the initial conditions again for attaining 0 and also L for your x and apply the conditions, then you will get again trivial solution, which means that actually again, it will be discarded. For minus alpha square, you get complex roots in your characteristic root, and you will get this result by initial condition. You get C1 is 0, but your C2, you will get, so for the L, you will get C2 times sine alpha L is 0, which shows you that if you take C2 is 0 here, then it will be trivial solution. So we will discard it again. But we say that it is different from 0. So I get the sine is equal to 0. Sine of something is equal to 0, which means that it will be sine of 0. But since the period here is pi, you will get alpha times L is equal to n times pi. It will be 0 all the time. So you get your alpha as this one. Remind that your lambda is equal to minus alpha square in this case. So you get an xn solution as the result of sine of n pi x over L. Okay? And after that, actually these steps are the same step that we do in wave. Okay? Wave equations. Since again lambda is equal to minus alpha square, just substitute it. So time equation becomes like that. You need to solve time equation here. You need to solve what is t of t function. To get that, again, you just write it as here the t part, here is the constant part, and here is our time variable. So this is actually, I write all these steps, guys. I'm rewriting them. Ln t and the right hand side again it will be integrated by respect to t, so you write that t times this expression. You need to add a constant a here. Say that for each n we get a result, so we write tn and an. So we write that if you write ln of t over a is equal to constant times t, you can write that t over a is equal to e to the t, e to the constant, sorry, e to the constant times t. So you get the final result here. As you see, tn is equal to an e to the minus k constant, I mean this part is constant, times t. So you can combine x and t, u was the multiplication of them, so you get the u value like that. You use the initial condition but not boundary, and also you say that for n is equal to 1 you get a solution, say that it is u1. For u2 again you get another solution u2, and etc. By the superposition principle I can add them up and get the result as the solution. So we say that uxt can be written as from n is equal to 1 to infinity for all n values, for 1, 2, 3, all n values we can add the solutions up. And after that, using the initial condition, we just only need to find our Cn coefficients, which is actually classical Fourier sine coefficients of f of x. Then, if you multiply both sides with a sine function that we see here and integrate over from 0 to L, 0 to L sine. We proved it last week for wave equation. This is the same. If you do the integration, then you will get sine square of the same argument, and we say that m must be different from n. If m is equal to n, we get a 0 directly, no solution appears there. So sine square n pi over x, we are analyzing this case, is equal to L over 2. So actually we isolate a single coefficient here. If you do the same for Cn, by this integration, you can get your Cn Fourier sine coefficient as you see Cn is here, it will be 2 over L from 0 to L f of x sine of n pi x over L dx. Okay? This process is the same like we do in wave equation. It's very similar. We found the Cn coefficients. So you are ready to write your uxt function. As you see, these are the Cn coefficients and the remaining part, so you get the result like that. What is this? This slide shows you that the classical solution of heat equation with homogeneous part. I said you that if it's non-homogeneous, some more complicated process and solution methods are needed, so we are omitting them. But we can switch to from Dirichlet to Neumann, Dirichlet to Robin conditions, but we are applying the same procedure, okay? But separation of variables will be used here, okay? That was the case and heat equation, and that's enough for us, guys. We finished the term. All the topic will covered will be the content of the final exam from the first lecture to the final. Again, like we say before, for the wave equation and also heat equation, we will ask for. We will not give you the Lambert solution or the solution that we obtain in the final slide. We will say that just derive the formula. So just understand the process what we do and do the same thing, okay? You will apply separation of variables. Just keep that. Maybe for lambda, you will analyze three cases and you can write in short that for lambda is equal to zero, a trivial solution exists or not, but you need to know the general process, okay? Hocam sınavda bu verdiğiniz final formülü yok. Fatih, generally we ask for derived formula. It is also valid for D'Alembert solution that we do for wave equation in the previous week, okay? Yes, you need to derive the formula. You need to obtain the formula in the exam. If you don't obligate, don't have an obligation to obtain the formula, we can give it in the exam. But generally, and also I discussed it with Coşkun Hoca, they ask for derivation of the formula. So just understand how we derive the formula for wave and also heat, okay? Bora, we will keep the same procedure. Coşkun Hoca also doesn't solve any extra problems, so I will just keep in the same level, okay? Actually, the solution type, I mean, the question will be the same, so you will just write some function instead of f. F of x will be 0 in simple, or it can be sine of x. So you just keep the derivative the same way, okay? So I will not solve it. Coşkun Hoca, the other section also doesn't solve it. I will not do that, okay? And that's all for guys. I hope it will be a good course for you. You learn a lot. We just covered all the topics algebraically. This is the content of the course, but we covered two wave equation and heat equation a little bit physically. I hope it will be useful for you. Okay. In the final exam, again, probably you will have four questions, probably 90 or 80 minutes. And that's all. Do you have any question? And then otherwise I will quit the class. Okay. Take care of yourself. Goodbye. Bye bye. İyi günler. Bye bye Tibian.